Ideal diode equation and derivation. A PN junction diode lets electric charge flow mostly in one direction. The current I that flows when a voltage V is applied is given by the ideal diode equation. I equals I sub S times open parenthesis e to the power of QV divided by NKT close parenthesis minus 1. Q equals elementary charge, 1.602 times 10 to the minus 19 coulombs. Think of it as the size of one electron's charge. K equals Boltzmann constant, 1.381 times 10 to the minus 23 joules per Kelvin, relates temperature to energy, like how much wiggle room particles have. T equals absolute temperature in Kelvin. N equals ideality factor, usually 1 to 2, that accounts for non-ideal recombination. I sub S equals saturation or reverse bias current, a very tiny current that exists even when the diode is reverse biased. Derivation sketch. Step 1. In equilibrium, no external voltage. The diffusion of electrons from N side to P side balances the drift of holes the other way. This creates a built-in potential V0 approximately equal to open parenthesis KT divided by Q close parenthesis times natural log of open parenthesis N sub A N sub D divided by N sub I squared close parenthesis. Step 2. Apply an external voltage V. It adds to forward bias or subtracts from reverse bias the built-in potential. Step 3. The minority carrier concentration at the edge of the depletion region changes exponentially with the applied voltage. Delta N is proportional to e to the power of QV divided by KT. Step 4. The diffusion current proportional to this concentration follows the same exponential law. Subtract the tiny reverse diffusion, negative I sub S, to get the net current, yielding the equation above. The -1 term guarantees that when V equals 0, I equals 0, no net current. For large forward V, QV much greater than NKT, the -1 becomes negligible and the current grows exponentially. When the diode's P side is made more positive than the N side, the depletion region narrows and carriers can cross easily. The IV plot looks like 3 zones. One knee, also called turn-on voltage, around 0.5 to 0.7 volts for silicon, the current jumps from nanoamps to milliamps. The term knee comes from the sharp bend in the curve, like the knee of a leg. 2 exponential region, above the knee, the current follows the ideal diode equation. A small increase of about 60 millivolts, for N approximately 1 at 300 Kelvin, multiplies the current by about 10. This is why a 0.6 volts forward bias can produce a few milliamps, while 0.66 volts gives 10 times more. 3 linear, also called resistive approximation, at still higher currents, tens of milliamps, series resistance inside the semiconductor and contacts becomes important. The IV curve bends upward and can be approximated by V is approximately V knee plus I times R sub S, where R sub S is the small signal series resistance. Analogy: think of a garden hose with a kink. Initially, the kink, which represents the depletion region, blocks flow. Once you straighten it, which represents applying forward voltage, water flows easily. And pushing harder, which represents higher voltage, just overcomes the hose's own friction, which represents series resistance. If the P side is made negative relative to the N side, the depletion region widens and almost no carriers can cross. 2 important behaviors appear. Leakage, reverse saturation current I sub S, a tiny current, pico to nanoamps, still flows due to thermally generated minority carriers that are swept across the widened depletion region. This current is almost independent of the applied reverse voltage until breakdown. Breakdown mechanisms: when the reverse voltage becomes large enough, the diode suddenly conducts a large current. 2 main types. Zener breakdown, typically less than 5 volts for silicon. A very strong electric field pulls electrons from their valence band directly into the conduction band, quantum tunneling. It behaves like a voltage regulator because the voltage stays almost constant while current rises. Avalanche breakdown, typically greater than 5 volts. Carriers gain enough kinetic energy from the field to ionize lattice atoms, creating more carriers, a chain reaction, like an avalanche of snow. Both breakdowns are destructive if the diode isn't designed for it, but specially doped Zener diodes exploit the Zener effect to provide a stable reference voltage. Temperature effects on saturation current I sub S and the whole V dash I curve. The saturation current is extremely temperature sensitive. It can be expressed as I sub S is proportional to T squared times E to the negative E sub G over KT. T squared factor comes from the increase of intrinsic carrier concentration with temperature. More electrons are thermally excited. E to the negative E sub G over KT term reflects the probability of an electron acquiring energy equal to the band gap Eg, approximately 1.12 electron volts for silicon. As temperature rises, the exponent becomes less negative, making I sub S grow exponentially. Consequences on the I-V curve. At higher T, for the same forward voltage, the current is larger because I sub S is larger, and the exponential term e to the QV over nkt is slightly smaller, kt increases. The net effect is a lower forward voltage for a given current, approximately -2 millivolts per degree Celsius for silicon diodes. Reverse leakage current also rises sharply, which can be problematic in high-temperature environments. Real-world example. A 1N4148 diode forward biased at 10 microamps might need 0.65 volts at 25 degrees Celsius, but only 0.6 volts at 75 degrees Celsius. This temperature dependence is why diode datasheets give a temperature coefficient for forward voltage. Explanation: small signal dynamic resistance, R sub D equals NKT divided by QI. When a diode is biased at a certain operating point, I0 V0, and we superimpose a tiny AC signal delta V, the resulting AC current delta I is linearized around that point. The slope of the IV curve at the bias point is the dynamic or incremental conductance. G sub D equals dI over dV evaluated at V sub 0 equals I sub 0 divided by NKT over Q. Taking the reciprocal gives the dynamic resistance. R sub D equals dV over d I evaluated at V sub 0 equals NKT divided by Q I sub 0. Derivation: start from the ideal diode equation, ignoring the -1 for forward bias. I approximately equals I sub S times e to the power of QV divided by NKT. Differentiate with respect to V. dI over dV equals I sub S times Q divided by NKT times e to the QV over NKT equals QI divided by NKT. Invert to obtain R sub D. Example calculation. Given I sub 0 equals 5 microamps, N equals 1.1, temperature equals 300 Kelvin. KT over Q approximately equals 25.85 millivolts. R sub D equals 1.1 times 25.85 millivolts divided by 5 microamps equals 5.69 millivolts over 5 microamps, approximately equals 1.14 ohms. Thus, a diode biased at 5 microamps looks like a 1.1 ohm resistor for tiny signals. This concept is essential in RF mixers, detectors, and diode-based low-noise amplifiers. Ideality factor, N, quantifies how closely a real diode follows the ideal exponential law. It appears in the exponent as QV over NKT. Physically, N captures the dominant recombination mechanisms. N approximately 1, diffusion-controlled current dominates, carriers diffuse across the depletion region. This is common for well-manufactured silicon diodes at moderate forward currents. N approximately 2, recombination in the space charge region, also called Shockley-Reed-Hall recombination, becomes important, especially at low forward currents or in heavily doped junctions. Values greater than 2 can appear in poor quality or high temperature diodes. Effect on the IV curve: a larger N makes the exponential rise slower. For the same voltage increase, the current grows by a smaller factor. In a semi-log plot log I versus V, the slope is Q over NKT. So increasing N flattens the line. Analogy: think of a hill, the barrier. Ideality factor is like the steepness of the hill. A steeper hill, N equals 1, lets you roll down quickly, current rises fast. A gentler hill, N equals 2, makes you climb slowly, current rises slowly for the same voltage. Explanation: logarithmic plotting of forward V I curve to extract I sub S and N. To find the unknown parameters I sub S and N from measured data, follow these steps. Step 1. Measure forward current I for a set of voltages V, typically from 0.2 volts to 0.8 volts for silicon. Step 2. Plot natural log of I versus V using the ideal diode equation, ignoring the -1 term for moderate forward bias. I is approximately I sub S times E raised to the power of QV divided by NKT. Taking natural log gives natural log of I equals natural log of I sub S plus Q divided by NKT times V. This is a straight line, y equals a plus bx with intercept A equals natural log of I sub S. Slope B equals Q divided by NKT. Step 3. Perform a linear regression on the plotted points to obtain A and B. Step 4. Compute I sub S equals E raised to the power of A. N equals Q divided by BKT. Practical tip: use the region where I is much greater than I sub S, typically greater than 10 microamps, so the -1 term truly is negligible. Example: suppose the fitted line yields A equals -27.6 and B equals 40 per volt inverse at 300 Kelvin. I sub S equals E raised to the -27.6, approximately equal to 1 times 10 to the -12 amperes. N equals Q divided by BKT equals 1.602 times 10 to the -19, divided by 40 times 1.381 times 10 to the -23 times 300, approximately equal to 1.0. Thus the diode behaves almost ideally. Explanation: Exam type problem 1. Compute diode current for V equals 0.6 volts, I sub S equals 10 to the -12 amperes, N equals 1.5 at 300 Kelvin. First compute the thermal voltage V sub T equals KT over QV sub T equals 1.381 times 10 to the -23 times 300 divided by 1.602 times 10 to the -19, approximately 25.85 millivolts. Plug into the ideal diode equation, forward bias, so the -1 can be ignored because e to the power QV over NKT is much greater than 1. Current I equals I sub S times exponential of V divided by NV sub T V divided by NV sub T equals 0.6 divided by 1.5 times 0.02585, approximately 0.6 divided by 0.03878, approximately 15.48. Current I equals 10 to the -12 times e to the 15.48. E to the 15.48 is approximately 5.3 times 10 to the 6. I is approximately 5.3 times 10 to the -6 amperes, which is 5.3 microamperes. Answer: the diode conducts about 5.3 microamperes at 0.6 volts under the given conditions. If the -1 term were kept, the result changes negligibly because e to the 15.48 is millions. Suppose a reverse bias measurement gives the following points V sub R, I sub R. 4.0 volts 0.2 microamps, 4.5 volts 0.5 microamps, 5.0 volts 1.2 microamps, 5.5 volts 3.0 microamps, 6.0 volts 8.0 microamps, 6.2 volts 20 microamps. The Zener coefficient, also called knee sharpness, is defined as the voltage increment needed for the current to increase by a factor of 10, a decade. From the data we see, from 4 volts to 5 volts, delta V equals 1 volt. The current grows from 0.2 microamps to 1.2 microamps, roughly a factor of 6, not yet a full decade. From 5 volts to 6 volts, delta V equals 1 volt. The current grows from 1.2 microamps to 8 microamps, a factor of about 6.7. From 6 volts to 6.2 volts, delta V equals 0.2 volts. The current jumps from 8 microamps to 20 microamps, a factor of 2.5. Extrapolate to the point where a half-volt increase gives a 10-fold rise. Typical Zener coefficient about half volt per decade for a 5.6-volt Zener diode. Using the 2 points around the steep region, 5.5 volts, 3 microamps, and 6.0 volts, 8 microamps. Ratio equals 8 divided by 3, approximately 2.67 for delta V equals half a volt. To reach a factor of 10, we need roughly log base 2.67 of 10, about 1.73 times the half-volt interval, that is about 0.86 volts above 5.5 volts. Thus, estimated breakdown voltage V sub B are approximately 5.5 volts plus 0.86 volts, approximately 6.36 volts. A more precise method is to plot log base 10 of I sub R versus V sub R. The straight line region after breakdown will have a slope of 1 over K, where K is the Zener coefficient. Fitting the points 5.5 volts, log I equals 0.48 and 6.2 volts, log I equals 1.30, gives slope approximately 1.30 minus 0.48 divided by 6.2 minus 5.5, about 1.17 decade per volt, so K approximately 0.85 volts per decade. Extrapolating the line back to where I sub R equals I sub S, the leakage current, for example 0.2 microamps, gives the breakdown voltage approximately 6.3 volts. Answer: the breakdown Zener voltage is approximately 6.3 volts for the given data. Any method that uses the Zener coefficient to locate the voltage where the current starts rising sharply is acceptable. The key idea is recognizing the exponential increase and converting it to a linear relation in a log plot.